Airborne propagation, airborne radio wave propagation, as we said, can be analyzed using two tracks. We have the analytical or theoretical models or mathematical models, and we have the empirical models. Now, the empirical models. These models are based on measured data, based on actual measurements made in the cities, and use curve-fit equations. Equations can be extracted from the graphs or from the data by curve fitting. You know this from numerical analysis courses, curve fitting. To fit an equation in curve, to extract an equation from a curve. And also the equations are tied, or the models are tied to urban land use maps. They are the urban land use maps, how the land is used in the city, how many buildings are, for example, within 500 meters squared, what's the total area of the buildings within this area, and so on. This is the meaning of tied to urban land use maps. And also, if we want to use, of course, this model will be most suited to the place where measurements were made. But if we want to use it in another place, we have to use correction factors. We may have different buildings densities, or different building heights, or different building areas, or different distributions. So we need, or maybe different geography, have more mountains, for example, or more valleys. So we have to take all these factors into account. One of these models is Okumura signal prediction model. Okumura is a Japanese person. Okumura, he made measurements for the signal level in Tokyo for the frequency range of, as you can see, from 200 to 1920 megahertz, from 200 to 1.92 gigahertz, from 200 megahertz to 1.92 gigahertz. He also extracted various behaviors in several environments, giving suburban correction factors, because urban measurement would be different from some urban. So he gave correction factor for suburban areas. And also, as we said just a few seconds ago, he gave maybe the terrain will be different. So he gave correction factor for various terrains, if mountains, okay, if they are mountains or valleys or plains. His results were inconvenient because data were available only as curves, no equations. So Hata, also another Japanese person, Hata, he extracted useful formulas from Okumura measurements, and his model became to be known as modified Hata formulas. So Hata model, he tried to put the equations, the extracted, the curve fitting equations in this form: A plus B log D. A is not a constant, of course. This means that A does not depend on D, and B does not depend on D. D is the distance between the transmitter and the receiver. D is the distance between the transmitter and receiver. So A depends on the frequency, on the height, but not on the distance. And B also similarly can depend on the gain of the antenna, the height of the antenna, the frequency of operation, but not it does not depend on the distance. Okay, this is the Hata model. This is the Hata model, as you can see here. This is Hata model here. This equation. Okay, this is the equation. LCCIR. CCIR, the International Radio Consultative Committee, adopted this model to be international, to be used internationally. Oh, this is A. You can see this is A here, and this you will find that this is also A here. All of this is A. This is A. A is 69.55 plus 26.16 log the frequency, so we do not have distance here, minus 13.82 log HB, the base station height. So no distance here, frequency, base station height. Now B, the parameter B, is given by this equation. B is equal, so this is A here, this is A, and this is B here. B is equal 44.9 minus 6.55 log HB, the base station height. It does not have distance again. And we have log D. This is log D. We take log D here. This is log D. Plus also a correction factor for the mobile height. Factor for mobile height. In this equation is a frequency in megahertz F, where the frequency ranges between 100 and 1500 megahertz. D distance in kilometer, here D, or D here in kilometer. And the range of D is from 1 to 20 kilometers. HB, base station height, HB here. HB may range from 30 meters to 200 meters. AX as function of HM, as we mentioned, is the mobile height correction factor or correction function. HM is the mobile antenna height in meters, and the range is from 1 to 10 meters. You may ask how the mobile height may be 10 meters. Maybe you are in a building, in the, for example, third floor or the fourth floor, or on the roof of the building, or on a mountain, so the height might be okay. Modified Hata formula. We take LCCIR, take this formula here, we plug it here, as you can see, and we add to it correction factors. So this is this equation, and we add to it correction factors. S naught, suburban urban correction. This is factor used to predict for prediction that takes into account whether you are in the urban area or in the suburban regions of the urban area. And B naught here, B naught is correction factor for the percentage of buildings on the land. This, depending on the percentage of buildings on the land, this correction factor will change. And SKS is correction factor for the Earth's curvature. For the Earth's curvature, you put a value here to correct for Earth's curvature. Of course, Earth's curvature will be used when you use long distances D. Now we know from Fry's transmission formula here that P received power at the receiver equal P transmitted the gain of the meter. Of course, we subtract losses due to the feed line, and we have this term here, lambda over 4 pi r for a free. I'm talking about free space propagation here. 4 pi r, or if you want, all squared times g transmitter and so on. So let's concentrate on this here. This is the free space loss. So you can see that the loss depends on the wavelength, and wavelength depends on the frequency. So the loss is frequency dependent. We want to have an equation, and we will call this equation universal propagation chart, where the loss is frequency independent, does not depend on the frequency. So this can be generated by this equation. The incident wave on the receiver is equal to transmitter power divided by the area of the sphere, 4 pi d squared, times the gain of the transmitter. This gives the power incident, the incident radiation power density near the receiver, where the transmitter is d meters or d kilometers away. And as we know from electromagnetic courses, that here okay. This is the equation. This is the equation for the power density in terms of the electric field and the wave intrinsic wave impedance, intrinsic wave impedance. For phase space, it's 120 pi equal to 377 ohm. Now from this equation, E squared here, you cancel 2, and here we'll have 2. So, and you take Z naught to this side here, and you will obtain E squared is equal Z naught times PT GT over 2 pi D squared. You can see that the electric field equation here does not depend on a frequency. That's we call it universal here. And here, this is the same equation as this I have already written. P received equal P transmitted, G transmitted over 4 pi D squared times, this is the effective area of the receiver. Now we introduce this definition, P transmitter times G transmitter is EIRB. We already talked about that during the satellite session, satellite communications, radio propagation. That's effective isotropically radiated power is simply is equal the transmitter power times the gain of the transmitter antenna. Okay, the loss, the free space loss is given by this equation, lambda over 4 pi d squared. Lambda is the wavelength and the distance between transmitter and receiver. Lambda is equal, if you put instead of lambda here, lambda is equal C of F, speed of light times the frequency. So cancel lambda and C over F, and you will obtain this equation, C over 4 pi dF squared. This is the free space loss. In dB, you take 10 log of this L. So 10 log squared, it will be 20 log. C over 4 pi multiplication be addition in logs. So 10 log C over 4 pi times, it will be now addition plus 20 log 1 over dF. As you can see. So 1 over dF will go here. You can say it's 1 times 1. So this times this, log this times this is log of this plus log of this. Now C over 4 pi, C, we introduce the value of C, 3 times 10 to 8 meter per second, and we obtain this to obtain this value. Here you can see 3 10 to 8 3 10 to 8 divided by 4 divided by pi is equal log this value times 20 is equal, you can see here, it is 147.56 approximation. Now D in this equation is in meters and F is in hertz. If we want to put D in kilometer, we multiply by 10 to 3. If we put F in megahertz, we have to multiply by 10 to 6. So now so this is 20 log 1 over D times 1 over F is minus 20 log D minus 20 log F. Okay, and D is in kilometers and F is in megahertz. We take also the log of this, 10 to 3 times 10 to 6, 10 to 9. It will be 10 to minus 9 when you take it then in the numerator. 10 to minus 9 times 20 is minus 180. So minus 180 minus 180 minus also plus 147.56 is equal minus 32.44. we can see here it's minus 32.44. so this is the free space loss. This is the free space loss. This is free space loss. Or the free space. Okay. Definitions here. E in dB microvolt per meter is 20 log E divided by 1 microvolt per meter. 1 micro is 10 to minus 6. 10 to minus 6, when it will go up, it will be 10 to 6. 6 times 20 is 120. So E dB microvolt per meter is equal to 120 plus E dB. And if you want to use E dBm, the difference would be 60. Because dBm is 10 to minus 3. 10 to minus 3, it will be 10 to 3. 3 times 20 is 60, and you subtract 60 from 120, it will be 60 here. So 1 volt per meter is 10 to 3 millivolt per meter. That's the difference. This is modified Hata model here. Okumura data is given by these crosses here, and the Hata model is the equations are drawn here. The curve fitting equations are these smooth lines. So this is here the horizontal axis is the frequency in megahertz. This is log scale. 10 megahertz, 20 megahertz, this 20 megahertz. This is here 30 megahertz, okay. This is 30 gigahertz here, and this is 40 here, 50, 60, 70, 80, 90, and this is 100 megahertz. This is 200 megahertz here. This line is megahertz, 100, 400, 500, 600, 700, 800, 900, 1000. And here we have 2000 megahertz, 3000, 4000, 5000, 6000, 7000, 8000, 9000, and 10,000, just 10 gigahertz. And the vertical axis here is the loss in dB. This is the loss in dB. This is not free space, of course, urban propagation loss, urban area. The base station height is 200 meters here. The base station height is 200 meters. Base station height 200 meters. And the mobile height is 3 meters. And this represents the distance between the transmitter and receiver. So this curve 400 kilometers distance. Therefore the loss is high. When the distance is lower, 60 kilometers, loss is lower. You can see here the range between 50 and 70. Here, when the distance is smaller, the range between 40 and 55 dB. And this for 20 kilometer distance. This is 5 kilometer distance. This for 1 kilometer distance between transmitter and receiver kilometer, the loss is lower, much lower, between 15 and 25. Here you can see this around 15 or maybe 16, and here you can see it's 15 and 26. But for large distances the loss is between 50 and maybe 69 dB. This is the universal urban area propagation curves. So this, when we put here the loss, it will be dependent on the frequency, as you can see here, frequency. But when we put here electric field, as we explained earlier, when the vertical axis is electric field, as you can see, this is electric field in dB microvolt per meter. There is no frequency here. Here it is range, distance, and we have here the height of the antenna, of the base station height, and that's all. And we get the E in dB microvolt per meter. After that, we put the E value here. We put the electric field value here. Okay, we put the E value here, and put the frequency, and to obtain the path loss. So it is a two-step process. We first find the electric field in dB microvolt per meter, depending on the antenna height, on the distance. Okay, and after that we put the obtained electric field here and the frequency to obtain the or to get the path loss in dB. I want to explain this here, this number. Field strength for 1 kilowatt radiated by a dipole. Now, how did we get 62.15 dB EIRP, effective isotropically radiated power? This is EIRP is PT times G. Okay, so it is in dB PT plus GT in dB, of course, plus transmitter power gain of the transmitter antenna in dB. 1 kilowatt in dB is 10 to 3. 10 to 3 is 30 dB. This is 30 dB. 30 dB, if you want dBm, it will be 60 dBm. This 60 dB. This is 60 dBm. Because 1 kilowatt is 30 dB, and you add another 30 because the difference between dB and dBm is 30 dB. So we will get 60. and the gain of the dipole is 2.15. Dipole gain, this is PT in dBm, and dipole gain GT is equal to 2.15 dB. So add the 60 plus 2.15, you will get what you will get. You will get 60 plus 2.15 is 62.15 dBm EIR. That's the idea of the universal curve. We have this equation now. I will stop here. I will derive this in the next session. I do not want this session to be very long. Thank you for listening. If you have any questions, comments, ideas, just let me know.